Thank you for attending our Water Research Center seminar series. And today we have Anna Barros, Dr. Anna Barros from Duke University. And so before we start the assisting her presentation, just please check in the chat box where you can actually enter your name and email in the Google form so that we can actually send out the information over our future seminar series. And so Tom, do you want to just introduce Dr. Anna Barros for our speaking?
My honor to do so. So we're really happy to have Anna Barros join our seminar today. Just give a little bit about her. She was born in Africa, in southwestern Africa, in Angola, and grew up there and in Portugal. She got an engineering degree at the University of Oporto, and then came to the US, got a master's degree at Oregon Institute of Technology, PhD at the University of Washington, and she is a professor of civil and environmental engineering at Duke University. She has received many, many awards and honors. Just name a few of those: the Borland Hydrology Award. She is a fellow of the American Association for the Advancement of Science. She's a fellow of the American Society of Civil Engineers. She's a fellow of the American Geophysical Union, a fellow of the American Meteorological Society, and many others. And she has a quite diverse research interests, and those that she lists are physics of water cycle processes in mountainous regions, with a focus on cloud formation and precipitation, which is something that's of big interest to us here in Hawaii. Remote sensing of the environment using microwave and infrared sensors, long-range predictability and risk analysis of natural hazards, another important topic for us, computational environmental fluid mechanics and nonlinear dynamics, and development and application of information technology as a research tool in the operation of complex engineering systems. So Anna, we're really thrilled to have you, and we're looking forward to your talk. Please go ahead. Thank you.
Thank you so much. So I know that Tom and Jim are experts in orographic precipitation and in cloud forests in Hawaii. So I had the privilege of visiting Jim's site. And so I'm really happy to be talking about this topic that is dear to my heart. And as you can tell from the long list of names at the bottom of the slide, so many students and postdocs and colleagues have really been involved in this experiment, the integrated precipitation and hydrology experiment, which started actually in the Southern Appalachians around 2007 when we installed our first gauges, and it's still going. Actually, our gauges are still going, and although the experiment proper, which was a ground validation experiment in support of GPM, the Global Precipitation Measurement Mission satellite, has actually concluded in 2015, the extended observing period. So what was interesting about this field campaign was that we could really plan it ahead. And so we started by developing a long-term infrastructure that consisted of rain gauges, which I'll show you later, and some other sensors. And then around the field campaign proper in 2014, just before and then after that, we had a very dense network of these hydrometers installed in the Southern Appalachians, which we continued to operate until 2016, along with micro rain radars and other sensors at various locations. So what I'm going to address here, today I'm going to talk about this as if we actually had not written a research proposal to get the funding. So I'm going to show basically the data that we collected, what we found, and how we actually developed hypotheses of how these processes were operating in this region, and actually everywhere, I think, where we have cloud forests and complex orography. And then I'll be showing some of the modeling results, and then of course looking forward, focusing on these interactions between the landscape, vegetation, and precipitation processes. So just a little bit of an introduction here. This is, of course, the map of the continental US. I'm sorry, Hawaii is not there. This little box here is basically focused in our region of study, which are the Southern Appalachians. And this is a zoom of that region. And so I'm showing this figure to give you an idea about where does the moisture come from and what's actually controlling the moisture convergence into this region. And because of that, it has actually a very important role in terms of what type of microphysical processes are important in these in different regions of the mountains. So most of the upper level moisture comes from the Gulf of Mexico or from the west. And then we have very strong input of low level moisture that comes from the Atlantic plains and from the Piedmont and gets into the inner mountain of the region of the inner region of the mountains, and so provides a very large moisture source that allows us to have actually cloud forests at very low elevations. So we have regions of permanent clouds at 500, 600, 800 meters, which would not be possible otherwise. So a lot of the storms then are coming from the west and from the south, and resilience actually comes from the east, because this is this low level moisture, as I'll show you later, is so important in terms of the water cycle, and it really means resilience to drought in this region. So in terms of the long-term monitoring, this is the system that we started with in 2007. So you see many different color symbols, and some of these stations were already in place, right? So some of them are part of the NOAA operational system. Some of them are part of the USGS system. Some of them are part of the North Carolina EcoNet. So what we did here when we came in was to really think about what processes are we going to look for. And so we were very interested in orographic precipitation. And just to give you an idea, the highest precipitation gauge at the time, east of 105, was at 1,000 meters. So we really did not know how much it rained at higher elevations anywhere in the eastern US. So what we did was to install the system of rain gauges that are the purple dots that you can see. And within each one of these regions, we identified different types of processes that we were going to be monitoring as they arrived. So in the west side, westerly mesoscale convective systems and fronts and atmospheric rivers. And then in the east, a lot of tropical cyclones like the ones we are waiting for now, also fronts and the convective systems in general. And then in the inner region, lots of fog, thunderstorms, the fronts as they move in from west and from east and from south. And of course, a lot of modulation of where the clouds form and where the rain forms because of the complexity of the terrain. We also installed a tower that was the highest elevation flux tower in this region of the country. And in addition to our rain gauges, we introduced MRRs, which are vertically profiling radars operating at about 24 gigahertz, and these drometers. One of the first discoveries that I want to emphasize here is that in the inner mountain region, about 50 to 70% of all the rainfall is very light rainfall. And by light rainfall, actually, this is not light rainfall at all. It's only light rainfall because we're so used to talk about rain in terms of units of depth per hour, right? So when we convert what we measure in units of millimeters or inches per hour, then the amounts of rainfall become actually very small. But in fact, we have very heavy, intense rainfall over very short periods of time. And so I want to emphasize that these processes are really important, and I'll come back to this later. The big mistake, and now my biggest regret, is that at the time, we had so much bias toward the high elevation measurements that we didn't place any additional rain gauges at lower elevations. And we thought we had no problem with that because we were going to look for the standard textbook type of orographic enhancement process. And so we didn't need to worry about the low elevations. And so this was a big mistake because as you'll see later, all forms in this landscape matter and play a very important role in the organization of clouds and in the organization of rainfall. So the first thing we did after we had this infrastructure in place was to look at the satellite data that were available before GPM, which was the TRIM rainfall mission, and do some aeroclimatology. And the typical aeroclimatology that we did here that was a little bit different from what is typically done when we think about rainfall and rainfall fields is that we looked at different aerometrics in terms of diurnal cycles and in terms of seasonality. And so one of the things that we found is that when we look at those three different regions that I identified in the beginning in the previous map, and we look at, for example, false alarms, that is when the satellite says that it's raining, but actually no rain was observed. What we found was that there was actually a very specific, these values were very high in the inner mountain region, and they were very high at a specific time of day, meaning they had a very well-defined diurnal cycle. And this was actually indeed true if we looked at mist detections. But in the case of mist detections, you will notice that the peak was actually a little bit before that. And you'll see later on that this is actually important. And then, we can look at this in terms of seasons. And again, the inner mountain region plays this very important role in terms of aerometrics that we had not imagined before. Now, recently, we have conducted similar type of error analysis with GPM. And we can also develop similarly the same type of analysis. And in this case, what you see is the spatial organization of error. In the case of the top map, this is frequency bias. And so these areas where the frequency bias is very low, it means we have very high false alarms. And those areas, as you can see, they are all in the inner mountain region. This is a map of the probability of detection climatology for March, April, and May. And this is important because this is when the mesoscale convective systems from the west come in. And as you can see, we also have these very low areas as expected, which is consistent with our frequency bias in the inner mountain region. So then the question is, what is happening in the inner mountain region? So we see seasonality in the errors, we see a diurnal cycle in the satellite errors, and we see a spatial organization in these errors. And so what this means then to us is that we have this complex orography and there is spatial and temporal heterogeneity of microphysics. That's our hypothesis. And it's because of this spatial and temporal variability in microphysics and in the vertical structure of precipitation that we see these kinds of patterns in the errors. And so the idea is how can we then understand what's going on? So here what you'll see, these were our first Sentinel stations actually from work that my student Anna Wilson did for her PhD. And so here we have a pair of ridge and valley locations in a relatively wide valley. And here, this is another ridge that is another ridge location that is co-located with our flux tower at Purchase Knob. And actually, in this location, we have one of Jim's fog gauges. Actually, we have several of them installed across the national park. And I should say thank you to Jim for having helped us at the time and for teaching my students to actually build them and manufacture them and so on. So that was a very important contribution, best measurement ever. So, and it was very important for us here, as you'll see later, I'll have a result that was only possible because we had one of the Juvik fog gauges working at that location. So in this case, what I'm showing here, so these are results from our these drometers. This is at Ridge 1 where we had our flex tower. But I'd like us to focus on these two here because this is the pair ridge and valley in the wider valley that I showed you before. And the thing that I wanted to emphasize, and there are two aspects here that I want to emphasize. One of them was that when we started looking at our dysdrometer data, we realized that we were collecting rainfall data that was actually significant. If you draw the cumulative rainfall curve at the valley, for example, and yet our rain gauge was not detecting any rain. So this was one of the first puzzles that we had. But also, what would happen is, I apologize, this figure has an error, a shifting error. But the other thing that we noticed was that at the same time, right, the measurements in the ridge were actually much fewer in terms of the concentration of drops that we were measuring. And so we had much weaker or less rainfall measurements for these very, very small drops in the ridge at the same time that we had these large numbers in the valley. The other important phenomenon that we found here, though, was that in the days when we had a convective system going through or a stratiform system going through, what actually happened is that when we had these sorts of measurements earlier in the day, then later on, a little bit later, we would have much heavier rainfall in the valleys than we had at high elevations, but significantly higher rainfall. And so the question is, what is happening? How can this be, right? So this is basically turning upside down what were our expectations. So before I move, I want to show you a little bit of this climatology of clouds in this region that was done by my former student, Viola Duan. And so this is from 10 or 12 years of MODIS data and looking at low-level clouds. So we're looking at clouds that are in the lower 5 kilometers. And so we actually have this for all seasons at all times. And here I just picked a few different fields to give you an idea of the spatial organization, also of the seasonality of these clouds. So when we look, for example, at the summertime, we see what we would expect. You see all of those beautiful pictures from the Appalachians with beautiful cloud decks everywhere. And this is basically what we see. The scale here is the number of days per season, actually in that season, this is not per year, it's actually per season, that MODIS detected clouds at this specific pixel. So you can see that in the summer, we have clouds basically on every ridge, almost every 2 days out of 3 or so. Whereas, for example, when you look at the nighttime, what we see is that we have very few clouds in the ridges, and basically we have fog and low-level clouds in the lower elevations around the mountains. In the winter, we have a very different behavior, right? In the winter, we clearly have a west to east sort of split, with the upwind side being the side here, and this would be kind of the rain shadow side. One interesting aspect here that I'll just move on quickly is the impact of the dams of the TVA in the spatial organization of cloud fields. So you can see the effect of the afternoon rolls and lake breeze effects in the organization of these clouds here. So we know we have these cloud systems. We have these fog banks, we have these low-level clouds all the time here. And so before I also move on, I just want to think a little bit into how do these clouds develop and how the associated rainfall develop, because I'm going to use some of these terms throughout the talk. So we're thinking here on this side of aerosol available in the atmosphere. This aerosol is mixed and it's entrained and moves up. At some point it's activated, and this is where we have our cloud base basically forming. And so after that moment, condensation is occurring on those activated aerosol. These hydrometeors grow, they mixed with air from the outside via entrainment and so on. They start colliding with each other, and some of them stay together and coalesce and form larger cloud drops. Eventually, they get big enough that they start interacting more effectively with each other and start falling faster. And at this point, then we have raindrop sizes developing. And through the column of rain, we have this competition between coalescence and breakup, right? So drops are colliding and coalescing all the time. As they get very big, they break up and so on until we have this sort of dynamics going on. As the rain comes through, if there are low-level clouds, for example, or fog, then what we see are these interactions between the rain that is coming from the major cloud system in this case, and the hydrometeors that are available here at low levels. This interaction is predominantly of this type, of a coalescence type. And so basically what it does, it fattens the drops. That's what it does. And it fattens the small drops. And it's incredibly effective at doing so. And these are what we call seeder-feeder interactions, where the seeders are the hydrometeors coming in the form of rainfall, and the feeders are these low-level cloud systems and fog. So in this system, we have vertical updrafts going this way, downdrafts coming this way, and SFI at the end, basically as our enhancement mechanism. So I'm actually going to do something here because I don't want to show this yet. So I'm going to show you first this data. So these are the data from the two locations that I was showing you before, where I said that we were very puzzled that we were collecting so many drops, measuring so much rain, actually so much water, and had no measurements in the rain gauges in the middle of the day. But also that at other times we had much higher rainfall intensity in the valley than we had in the ridge for the same exact system. So these here are cross sections from an MRR, a vertical profiling radar, and these are heights above the ground level. And so this is in the valley. We had one, and we had one in the ridge nearby. And so what we did with this was to actually develop a model that simulates the processes I just described in the previous slide. And so to give you an idea about what's going on in these figures, this is on a specific day in July of 2012, and it's in the early afternoon. And so the blue line here is the measurement of the cumulative rainfall curve from our disdrometer. The green line is the same cumulative curve from the rain gauge that is collocated with that disdrometer. And so you can see that here in the beginning, the rain gauge is detecting much less rain than our disdrometer is. And then these two lines, the brown and the black, these two here are the rainfall inferred from the reflectivity of the MRR, just using normal ZR relationships. And so you can see that if we use the typical recommended, what used to be recommended 15 years ago as the gate that one should use to retrieve rainfall rate from an MRR, we would be getting rainfall that was really, really very low. And so we would be missing all the structure that is in the lower 1 kilometer of the atmosphere, and actually this enhancement here at this point. So if we use a slightly lower gate, which is actually a much lower gate, we have much higher rainfall, but we still cannot match the observed rainfall at our rain gauge. So what we did then is we added in this model of cloud microphysics and of rainfall microphysics, what you see here is in this red line is the model with the boundary condition based on the 1 kilometer reflectivity values from the MRR. And then the black line is what we can actually simulate if we introduce seeder-feeder interactions. So if we have a representation of the low-level clouds and fog and those interactions between the different hydrometeors. And as you can see, this is a difference in terms of rainfall estimation of about an order of magnitude. Now you could say, well, you don't really need that, or the model is really not that good, but we can do the same simulations, right? And in these simulations, there's absolutely no calibration, right? This is purely, strictly physics, by using the same top boundary condition and simulating the same microphysics over the ridge. And so what you can see is that the model gets actually pretty well, right, the rainfall evolution over the entire period of time without the need for any adjustment for seeder-feeder interactions. So this is sort of an indirect way of demonstrating that indeed these seeder-feeder interactions are necessary to be able to get and produce these sorts of very high, short duration, high rainfall intensities that we are observing in the inner mountain region. So focusing on that then, when we conducted the IPHEx intense observing period, there was a focus. I really was very interested in looking at this issue of how come we're forming these very stable fog banks and cloud banks in the inner mountain region, and what's the role of aerosols in maintaining those clouds, and how does this interact with topography and so on. So we had a super site in the inner mountain region where we had a W band radar, we had a KA band radar, had rain gauges, these hydrometers had a PCASP, which basically is measuring very small size particles, had an SMPS and the CCN counter, had a microwave radiometer, so we could get vertical distribution of liquid water content in the atmosphere. This is a 2DVD hydrometer. We also had a ceilometer it's in here somewhere in one of these. And in addition, there was this aircraft, the University of North Dakota Citation, that was equipped to go in and fly in spiral when there was rain or certain types of clouds, so we could get information on the vertical structure of microphysics in this area. And so just to give you an idea then at what the range of hydrometeors that we were measuring, this is from our mobile observing platform, which we call it from haze to fog to rain. Basically, we were looking at everything actually between 0.1 to any size of raindrop using different types of instruments. And in addition to that, so this is, this size here, which corresponds to haze and gives the Great Smoky Mountains the beautiful colors they have, actually corresponds to the aerosol accumulation mode. So if we think about the size distribution of aerosols associated with these events, then we can see that we have raindrops basically forming at sizes greater than about 10 microns. Between 0.1 and 10, we have this sort of transition between haze to fog, drizzle, and eventually rain. Here on this side, between 0.1 and 25 nanometers, that's when the aerosols are getting wet and being activated. And below that, we have the Aitken mode and events such new particle formation and so on. We're not going to talk about a lot about this, although this is actually important when we'll be referring to the role of ecosystems in this region in terms of helping us understand what goes on in terms of the spatial distribution of rainfall. So these are actually measurements that were collected then at this Maggie Valley super site. So this is for a couple of days, just so you can see how these hydrometeors actually start, right, with a very new particle, right? That is, in this case, we argue that this is an event of new particle formation, possibly of biogenic origin because of the forests in this area. And so as these particles form and they grow until they reach the accumulation mode, then at that point, if we have the right amount of humidity, the right conditions locally, then what you'll see is that these aerosols get wet and they start growing into haze and eventually into fog. So these different instruments are actually following the evolution of these hydrometeors over time, right? And one thing that I wanted to emphasize is the importance, again, remember, I showed the first results with the, I wanna make sure that I keep track of time. I showed our first results with emphasizing the middle of the day conditions, right, in the inner region. And so eventually, all of this is interacting, right? And in this case, we had also a rain gauge, of course, in the dysdrometer. And what we see, though, is that in the middle of the day, which are these areas here, this is our micro-rain radar measurements. These are our dysdrometers. The rain gauge sees nothing, right? The dysdrometer is actually collecting drops that are associated with these. We have 1, 2, 3, 4 different sensors measuring drops, and even the radar is detecting some cloudiness, right? Activity, but the rain gauge doesn't see anything. And then, and this is what it looks like locally. This is what this, that we're measuring here looks like over, basically wrapping other ridges and coming from the valleys up and forming actually pretty, 300 meters, 400, 500 meters of deep low-level clouds and fog. But then you see that later on in the evening, we actually have a rainfall event, which is very well captured by the rain gauge. It's well captured by our parsable dysdrometer, very high concentration of drops with very large drop sizes, right? So now we're talking about raindrop sizes on the order of 3 millimeters or so. And so for those drop sizes, when we have rain with this kind of drop size, then our rain gauges are actually measuring what's happening. So this is all the rain that's not measured. And of course, this is what's being captured by the vertical profiling radar. Okay, so in general then, when we look at this region, we have the Black Mountains and of course, all the way here, the Blue Ridge that you probably have heard about, the Smoky Mountains on this other side, and then in between the inner region. So here we have along the Black Mountains, there's a pretty persistent bank of fog. And so the trees here are permanently immersed in the cloud, very much like what Jim had in his site. And here are the results actually at a different location though. This is in this area here, roughly here, where we actually measured. So this was during the experiment. So this fog measurement was collected with one of Juvic's fog gauges, okay? And this is what a collocated rain gauge was measured at the same time. And so what you can see is that during this period, because of course we planned a precipitation field campaign with 3 aircraft and hundreds of people involved in this, and then it rained very little, right? So we had to go measure over the ocean and measure in many different places for the aircraft to be busy. But what was interesting here is that you can see at this location, which is one of those locations where in the summer, there's a cloud immersion or cap clouds 2 days out of 3, what we see is that the rain or the precipitation, not the rain, the precipitation that came in the form of fog is actually twice as large as the precipitation that was measured by the rain gauge. And I don't have that here, but actually all these measurements, they also have a different diurnal cycle. So these measurements are between, say, about 5 a.m. and actually 11 a.m. at this particular location in the mountains, and then later in the evening, whereas the rain is actually happening in the middle of the afternoon. So we have, in this case, this very small, lateral sort of precipitation that is being measured being way more significant, right, than the rainfall, and with a very different diurnal cycle as well. And so you can imagine that at these different locations, what we find is that the ecosystems locally are very dependent on these changes, on these diurnal cycles. The other thing that I wanted to show here is the importance of the seeder-feeder interactions on the rainfall that we observe. So typically when we think about orographic precipitation, we're thinking somehow that we expect a dependence with elevation. The dependence with elevation exists in the Southern Appalachians, but it's actually very weak. What we see if we have a frontal system coming, which is like this event here, then we see that the disdrometers in the valleys are in the ridges, they all measure the same thing. So this is just a system that's going through, right? And it's damping water. It's interacting very, very little with the local landscape, except for local modifications. But when you look at the southern event here, this is a locally generated rainfall event. And in this case, you can see that the two locations in the valleys are actually recording twice as much rainfall as the two locations in the ridges. So we started talking about this reverse orographic effect at the time that you see in this mountain region, but in fact, you see it in many coastal areas and in many low elevation mountains or middle mountains that have lots of moisture available to them. Now, as a result of this experiment, we also collected CCN information, right? And I can see already that I'm not going to have enough time to maybe go through everything, but I wanted to show you the importance of the collection of CCN or aerosol measurements at the same time as we make measurements of rain. So in our super site, we collected data through the entire period, and I'm showing you here two curves for the supersaturation versus number of CCN that were activated at this location. And these curves that you see here, the continental curve and the maritime curve, I always use them because they have been for many years used as the reference aerosols that I use in numerical weather prediction models and in many climate models to represent continental aerosol versus maritime aerosol. So I guess this would be Hawaii's aerosol. But so the difference you can immediately see here is that for small changes in supersaturation here, in the green and in the red curve, we have a very fast activation, right? We have a very fast increase in the number of CCN being activated. This makes all the difference because as soon as this happens, we start have changes in condensation rates, which means we have changes in latent heating profiles in the clouds. And so basically the whole thermodynamic environment and so on of the precipitation system changes. And indeed, I want to show what are the impacts of these changes by showing you these are some model simulations with the weather research and forecasting model. Then actually some time ago when Viola defended her PhD. And so we had a nested grid at 1 kilometer resolution here in domain 3. And I'm going to show you some results that are calculated or are presented for this cross section along the ridge area here between D and D prime. So going from west to east in this region. And so the focus is going to be on comparing, right, what things look like when we have the regular standard aerosol or when we have the aerosol that was measured locally that we know is representative of the cloud condensation nuclei locally. So just to start with, to compare, these are measurements conducted with the UND citation aircraft, and these are the numbers of drops that were measured at different heights. And so the aircraft is flying in spiral on this through this cloud system. And so what we have here are the cross sections that I just showed you from east to west. And this is for the control aerosols. This is using the IPHEx aerosols at 2 different levels in the atmosphere, at 3 different levels in the atmosphere. So around here, in this area. And just to give you an idea, the numbers of particles that are actually forming, right, are the numbers of drops in the clouds for the continental simulation are on the order of maybe 150 if we are generous. And yet we were measuring at those heights values as high as 600 or 700. So just by switching the aerosol type, we're not doing anything else in these simulations. By doing that, we can now get numbers that begin to approach, that are approaching these values measured at these heights. And so this shows the importance of getting the right type of aerosol, right? In activating the aerosols in the right way, because otherwise we're always running behind in terms of the time of rainfall. The other important effect of this, though, is that when you start looking at liquid water path, or basically how much water is there in the clouds, then there's a huge difference between the continental case and the IPHEx case. So we have significant differences in the amount of cloud water in the clouds, which have implications for the types of raindrops that we can form, and that can be shown here. In the case of the observations, we were actually measuring raindrops as high as 5 millimeters, but of course the models at most can get to 1.4 or so, and so this is one of the limitations where you can see the problems in the models, that we are really off in this way. But still, right? When we look at these cases, and now we're going to compare two different types of situations. This is still 11th and 12th of June. It rained in both days, but in one case we had a very strong synoptic forcing condition, and in the other case we had very weak forcing. And so you can see immediately that we have very different space-time organization of the clouds in this area. But again, we're measuring 3 to 5 millimeters drops, and the model is really only going up to about 1.4. Although we are forming larger drops with IPHEx. Another thing is that this is more extensive, but we cannot tell really much of a difference between the two. And so the question then comes in, okay, so you showed us that having different type of aerosol, because we have a strong impact on the activation, on how fast the aerosol are activated, it makes a big difference in the liquid water path, but so what, right? We didn't see very big differences in those rainfall fields. So what we did then was a simple experiment to separate orographic effects from aerosol effects. And so what we did here was to cut the terrain, or cut the mountains, basically creating a plateau at 600 meters, and then running both with the different types of aerosols and calculating the difference, right? And so what you see in this case is that by eliminating the terrain, or basically decapping the mountains, we actually introduce the same sort of change in the rainfall fields. These are differences between continental aerosol and continental decapped, and IPHEx and IPHEx decapped. And so we don't see significant differences. However, and so that's the effect of orographic enhancement. So that looks the same. It doesn't matter what, right? But when we now look at separately the effect of the difference between IPHEx and continental aerosol, then we start seeing the impact of actually even the synoptic forcing, right? We see significant differences in the structure of the impacts. So, and what are the consequences of this, right? So I'm showing those fields, and we can see that in some cases we're talking about differences of about 50 millimeters difference of rainfall, maybe 75 in some cases. And but what does that actually mean in practical terms? Well, it means that in this case we have midday rainfall suppression and localized evening enhancement. So this is a significant difference in the type of diurnal cycle we have in this region. Because with the continental aerosol, we cannot get midday rainfall, and we have much weaker evening precipitation. And you can see that I am not going to leave some time for questions, so I don't want to get into a lot of detail. So if we just focus on these graphs here on the left-hand side, you can see here the vertical structure of the mean mixing ratio. So of different types of water mass in the atmosphere. So the orange is the cloud water mixing ratio. The green, the blue is the Grapple mixing ratio, and the red is the rain mixing ratio, and the purple is the hail mixing ratio. So this is a microphysics parameterization that we're using that has these different types of ice processes. But what it really shows, again, that I had already shown before, is that when we use the IPHEx aerosol types, then we have much more water in the clouds than we have using the continental aerosol in this particular case. This is midday. And you see that actually in terms of the numbers of the different of cloud particles or cloud hydrometeors and rain hydrometeors, we don't see a lot of difference in terms of the rain in this case, but we see in terms of the cloud. So now if we go to another day, and we're focusing now here in the evening, right? We looked at before was this midday suppression of rainfall and of clouds in the model versus now what happens in the evening. So what we see in the evening is also the same thing. We have the cloud water. And now let us focus just, basically on the cloud water. Again, we see that we have a lot more cloud water. And now let's focus on the Grapple specifically. So you saw here that the difference between IPHEx and continental was very small. This is in the middle of the day. So these are warm rain processes for the most part. But at the end of the day, we have a convective system. And in this case now, the difference is actually very significant in terms of how much of the water mass in the cloud is actually in the form of ice, which then has implications for the melting of ice and latent heating profile in the atmosphere. So has huge impact on the vertical structure of precipitation locally, just in terms of a local thunderstorm. And then here, this is just a summary of the impacts on our diurnal cycle, impacts at nighttime, and also in terms of intensity. And I'm not going to spend a lot of time on this. What I wanted to show is now the linkage between those two conditions, right? All these impacts of having more or less water in the clouds, and in this particular case, having more clouds in the case of the IPHEx, of using the IPHEx aerosols. And what does that mean for the surface energy budget, right? And so we're going to focus on that particular time. And what you see here is the difference in surface, in the temperature of the surface between 14 and 16 local time, so between 2 and 4 p.m., between the continental and the IPHEx case. And so what you can see is that over some locations, we have differences as high as 5 degrees, And so this is huge, right? Because what this means is that you have huge impacts on evapotranspiration. We have huge impacts on long wave radiation. And you can see that's actually very different depending on, of course, the synoptic conditions. Why is that? Because the convergence patterns are different. So the clouds that form are different, right? And because the clouds are different and they have the liquid water path is very different. In this particular time, we had very small difference, whereas here we had very strong features in the case of the strong synoptic forcing. Then we have a lot more patchy situation, but still very significant differences in surface temperature, right? And so this is just in one day, in one afternoon. And so this explains why there's literature from the 40s and the 30s in the Great Smoky Mountains, where people would say that they measured differences in surface temperature between just adjacent slopes on the order of 13 to 20 degrees in some cases. And so when I first read that, I thought, that cannot possibly be, that seems like too much, right? But you start realizing that if we have persistent clouds over these locations, then we completely change the surface energy budget and what goes on in these regions. And by the way, the model is predicting this, but the model is not simulating, because these models cannot do low-level clouds and fog. They actually cannot simulate those. And so because those are not really accounted for, then we're actually underestimating this impact, of course. So we cannot really immerse cloud forests in this way. So we looked at all of these data, and instead of starting with the science question, we're actually going to the science question, which is really then what came from looking at all of these data, and that is, what is the influence of the aerosol physical and chemical properties on fog, on cloud development, on warm season precipitation evolution? This is what we know, right? This is what we can see. That's beautiful. This we can see too. This is a photo from a Purchase Knob. But actually, how do these aerosols come here? We have really benefited from the Clean Air Act, and so the decrease in pollution and in aerosol that used to come from Ohio and from other places into this region is really down. And so what we now are focusing on is on these interactions between the ecosystem and these trees, right? The volatile organic carbons that they transpire or emit, and the role that might play in terms of formation of aerosols locally. And so this is actually measurements of isoprenes, which are biogenic, which are of biogenic origin, and this is a location in the Great Smokies. And what's interesting about this is really sad. So you plan this huge field campaign. We learned so much, so it's not sad. It was actually great. But as you can tell, this was the year when we measured, when the lowest amount of isoprenes was measured. And this was actually during the year of the experiment. So we believe that we have a water-stressed forest at this time. But in other years that were really wet, you can see that when we have lots of rain locally, especially lots of midday rain, we actually have very high emissions of isoprene, measured in those years. So the question then is, what are these interactions, and how proactive are these ecosystems in capturing their own, or harvesting their own precipitation? And so I'm going to stop here. I was going to go to show something else, but I think we should have some time for questions, and I apologize, I went too long.
Thank you so much, Anna. That was really nice. We do have time for some questions. Some people may have to drop off to go to other things, but we can continue for a while. And I asked Harry, if you don't mind, I asked John DeLay to read questions from the chat. So if you have questions, please put them in the chat and John can read them out. I think that's the best way to go forward with this. So if you have a question, please put it in the chat.
Thank you, Tom. I see that a couple of people had raised their hands. We have one here from Michael Burnett, and he says, thanks for the great talk. I'm curious how the WRF model was able to simulate orographic rainfall in your study area with and without the IPHEx aerosol measurements.
So
go ahead.
So the question, actually, could you repeat the question?
Yeah, sure. So he's interested in how the WRF model is able to simulate orographic rainfall in the study area with and without the IPHEx
so
measurements.
independently of aerosol, right?
Oh, well.
How does it do, basically, right? That's the question, I think.
How it performs, with and without.
Yeah,
that's the question.
I could even get out of end slideshow because there's no need for that now, and I can just go there. So what we do here, of course, we've been working on this for a long time, right? And so actually, there's a paper in Journal of Hydrology from 2015, I believe, where we experimented a lot with different parameterizations in WRF. But the model has lots of problems, but at least because we're using a very high resolution, a very high spatial resolution, and using these parameterizations, actually using milliband and yaw, and using a boundary layer, which is the MINN boundary layer. I should add it here for people who might be interested. So for this combination of microphysics, we were able to get very, I would not say very good, but I would say physically meaningful simulations of clouds and rain that we could compare with our observations and make sense. So what we could never really do was to simulate low-level fog and clouds to the extent that they are observed. Does this answer the question?
He says, thank you.
Okay.
Yeah, it does. Thank you.
Okay, good.
I know Stephen had his hand up at one point. Here it comes. He says, looks like the IPHEx aerosol model has a lot more particles, but lower solubility than the standard continental model. Is that the basic difference?
We actually, so regrets, right? I feel like writing another regret. So, it's interesting because we finished this field campaign 4 years ago. We're still publishing, of course, with some of these results and so on. The data are publicly available, so anybody can use, this data. They're all available from NASA, from the NASA IPHEx website. But one of the limitations of this was that we didn't actually collect chemistry data. So we don't know the composition of these aerosol. There are lots of aerosol measurements in the past in this area. So we don't have that specifically, but we do have are the measurements from this from Marcus Petter's setup in the lab, right? Where basically he's extracting aerosols, he actually dries them and then he slowly wets them, so we can determine exactly the supersaturation at which they become activated. So this is not my expertise, but but he's a professor at North Carolina's State University, and so it was using his data that we could infer these curves. And so basically what they show is exactly that, is that they uptake water much faster, right?
He says, yeah, I know, Marcus.
Okay. Marcus is great.
There's any last question? Maybe since there's just a few now, maybe we can just have you raise your hand or, just turn on your mic and ask. John.
Oh, hi, Anna. Thank you. I'm curious about the fog gauge part of it. It looked like in that diagram for P2 or something, that it looked like two louvered screens on their sides. Was that the fog gauge?
Is this the picture you're talking about? This one?
I was actually not looking at the data. I was interested in how you deployed the instrument itself.
Okay. So,
and I think in P2 or something in the campaign 2014, I thought there was a picture there, and it looked like two of those louvered screens lying on their side there.
Here. This one, maybe?
Yeah.
Okay. Yeah. So what we do is actually, this was done pretty carefully. So we install them far apart, so we don't have the influence of the. As you can see, the gauge is on a pole, right?
Mm-hmm.
And so we actually secured those. I don't have a picture here, but we secured these, quite far apart. But of course, looking for a common, flat area. And this one is more this the 2D dysdrometer, which is really, this one is actually taking photos, right? So this one is counting drops as they go through, right? And this one is actually filming them.
Wow.
And so this one is actually counts more efficiently than this one does, although this one gives more accurate measurements of the sizes. So here we have a paper where we go into the issue of large errors when you have many small drops, and so that's a real problem with these parsable to
evaporation from the surface.
Yeah, exactly. So we did some lab experiments and everything with that. Now, this PCASP only works when it's not raining, and what's actually measuring is wet particles, but if it's not raining, so they have to be very small. If it starts raining, we had a little ceiling, that we would pull to cover this this instrument. In this case, what we're trying to see, this is basically just a trailer with all of these sensors on top, but we would take this out of this. So we have the pole for the rain gauge there. This is the PCASP, but the dysdrometer would be outside.
Thank you.
Yeah, to make sure that we don't have a lot of interference. I have to say, our experience with his, I don't know if I have here if I don't have here, I could show you from another location. So in this area here, we had at one point almost 60 of these dysdrometers spatially distributed here. And so we tried to be as deliberate as possible. And of course, we designed some transacts that we thought were going to measure specific types of microphysics. But this area here is very, there's lots of small towns and people living everywhere, right? So it was not easy to find a place that was ideal. So we eventually found one at the lower elevation, and we put a little fence around our site, and we had two dysdrometers collocated. And we had one above the fence and one below the fence. And you have no idea the impact it had on the measurement. That's when I realized how sensitive these measurements are to wind effects.
Wow.
It completely changed the measurements. And so in the middle of the afternoon, no, it was fine. But in the morning, because of the cold pool that forms at the bottom of the mountain here, right? And so you could clearly see the difference between the air that is moving above the fence and not moving below the fence at all. So the fence was acting almost like a wind fence, effectively, right? And which we didn't have in these disdrometers. And I have thought about this. So yeah, I feel like I'm talking about the experiment and it's all about regrets, right? But we should have done somehow some really careful measurements with different wind conditions to look at what is the impact on the disdrometer measurement. So I trust these measurements pretty well in the middle of the day, for example, but during times of reversal of winds in these valleys and in these mountains, then you have to be extremely careful, because if the wind gets very strong, I'm not sure that I'll catch. And as opposed to rain gauges and snow gauges, right? The WMO has not had any intercomparison study to characterize errors in disdrometers and so on. So we do what we can, and we really have to do it ourselves in a way.
Thank you, Anna.
Anna, this is really super interesting work. This is Tom speaking. Really super interesting. I know many people here at the University of Hawaii are interested in this work and are doing similar kinds of work here. And I encourage everyone to get in touch with you about this really fascinating.
No, I was thinking, that's why I was excited actually about, thank you for inviting me, about giving this talk, because I think you guys have a natural laboratory.
Yeah, we think so too. And
Right.
so we'd love to talk with you further. I'm going to turn it back over to Harry, but just to say thank you very much, and we're really nice talk, and we really appreciate you giving us your time.
No, thank you.
Yeah, thank you so much for attending the seminar. So we'll wrap up the seminar series, and then our next seminar will be the week for about the desalination. And again, thank you very much, Dr. Barros, for your great talk.
Thank you, everyone. Good night.
Thank you.
Bye.